Welcome to AI-powered calculus. We are taking a look at a function f of x is equal to x to the fourth plus x cubed minus x squared minus x divided by x plus 1. And we just want to march through chapter 1 of our textbook to try to get a solid understanding of what's going on with this function from a 360 perspective. So let's go ahead and take a look at what's going on. First and foremost, when you see the worksheet, it's AI-powered calculus. And this symbol right here that we have, let's go ahead and highlight that. This symbol right here is going to be a symbol that lets you know that we are about to get into some of the AI aspects of looking at calculus. But before we do that, we always want to make sure we have a solid mathematical foundation and understanding of what's going on. And so we're going to put pen to paper, pencil to paper, stylus to pad, and see what's what. So for this function, we want to figure out a couple of things that are important about it. First of all, let's take a look at this domain. We have different ways we can represent functions. We can represent functions verbally, graphically, tabular fashion. And here we have a symbolic representation. And so what's the domain of this function? We know that the domain of a function is anywhere where good things happen and bad things don't. So if you look at that function, the bad thing that can happen is that x plus 1 could be 0. So the domain is where that doesn't happen. In other words, the set of all x is such that x is not equal to negative 1. That's a set builder notation. Alternatively, we could put it in interval notation. Negative infinity to negative 1. Not included, union, negative 1 to infinity. Alrighty, that's in interval notation. Okay, look at your number line, and it's all good until you get to the value of negative 1. Right, so our domain is everything other than negative 1. Then if we think about it, that means that our function is defined everywhere except negative 1, right? So if we input negative 1 into our function, f of negative 1 does not exist, right? That's what this indicates. So we can say thus, or thusly, if you want to be suave with it, you can say f of negative 1 does not exist. All right. So that being the case, we could define a new function. You could say h like this. It looks like our original function everywhere except negative 1. When x is equal to negative 1, it's equal to our favorite value, right? Let's say 7. That's my favorite number, so let's call it that. This is what we call a piecewise function. It's defined in one way, in one location, right? And it's defined somewhere else in another location. And you have to do it on a case-by-case basis to understand what the value of the function is, depending on where you're at. Now, there's another definition related to functions that's going to be important for this function, and that is connected in what we have here with categories of functions. What do you mean when you talk about categories of functions? Okay, so as far as categories, and please forgive my mixing of uppercase and lowercase, I'm a mathematician, not a grammatician. So functional categories, I mean, we have a lot of different aspects, right? We have, of course, our favorite type of functions, polynomials. Right, and we're going to find out eventually that everything, just about everything, a lot of functions can be represented as polynomials of degree 1, 2, 3, all the way up to infinity. Okay, there's polynomials. There is rational functions. There is root functions, power functions. We have these as our algebraic functions that can be built from polynomials, right, and powers of x, so to speak. We have logarithmic functions, exponential function, trigonometric functions, right? I'm just doing this off of the top, so I might be missing something, but those are the main types of functions, right, that we deal with. Now, what type of function was our original function? This guy right here. Okay, this original function looks like a polynomial on top, a polynomial on the bottom, linear function, which is a polynomial on the bottom. And so therefore, any ratio of polynomial functions is called, drum roll please, a rational function. All right, so the function that we're dealing with, right, that we're rocking with for this entire worksheet is called a rational function because it's a ratio of polynomials.
All right, so welcome back to AI Powered Calculus, and we are going to take a look at the same function, the same rational function, and try to see if we can use AI and coding to help us understand a little bit more deeply some of the properties of this function. So first things first, looking at the function in terms of the domain, etc. Let's see if we can generate some code to tell us what the domain is. So I'm gonna hit generate with AI. And I have this very carefully curated text. Show me the domain of f of x. Use LaTeX so that I can see it in Markdown. By typing this specific text, what we will get is a typed out representation of how to find the domain and what the domain is. So this is the kind of text exactly word for word that you want to use when you step into this environment. And so let's go ahead and hit enter. And when we do that, it's thinking and it generates this output. So the text that we typed is called a prompt, and then the output is what we're going to go ahead and copy right here. Now, when you look at this output, it's kind of hard to read. There's a lot of dollar signs, curly brackets, and all of that. This is in LaTeX, and so you want to copy it and paste it into a text box. So hit text, paste. And then now when you render this, as you can see on the right, it is allows you to read. So it gives it the function, which notice we didn't tell it what the function was here. So that means that the AI is reading the notebook and it sees f of x up here. All right. And it says we can factor. So we can factor the polynomial. And then that's our numerator. We can cancel with the denominator, one of the x plus ones, and end up with this right here. But we know two things. First of all, that x equals -1 is not allowed in the denominator. And secondly, that when x is not -1, it's equal to this, which is a polynomial, which means it exists everywhere else. So the one problem spot is -1. We can take account of that, and here's our domain in set builder notation.